So this times I have the presentation in PDF. It is not PowerPoint. So I must admit I was not I didn't intend to present this in my visit, but from your interaction and based on the request of Professor Jalil, Professor Akhtar, I digged into my documents in order to see a good presentation about GPR and SAR. Some of you asked about giving some information about GPR and SAR. This has been presented in a workshop at IMS, International Microwave Conference, 2011. It was in Baltimore. The TPC is an Indian friend of me. You may name Ramesh Gupta. He was a TPC chair. These are my co-workers, finished a couple of years ago. He was my first PhD student in the late 80s. And this is myself. Okay, the workshop had about seven presentations, and this was one of them, covering some aspects of ground penetrating radar and SAR. The outline, after a short introduction, talk something about the motivation and challenges, the experimental ground penetrating radar setup, the necessary signal processing within the setup, the SAR concept, synthetic aperture radar, and I will show you some results. Before now going with the traditional way of presentation, I'll talk free. Let us first explain what is meant by SAR and what is meant by GPR. In my last presentation, we talked about antenna arrays and how the extension of antenna arrays or extension of the antenna aperture, whether this aperture is something like the dish you have for the TV reception, or the area covered by the elements of an array, this is called the antenna aperture. So how, over which dimensions the antenna elements are distributed, if they are discrete or if they are continuous like a dish, this physical area. By the way, you can very, very easily prove that the antenna array is an application of the sampling theory. Okay? In other words, if you have a continuous antenna like a dish, this is now the entire aperture, radiates or receives. So if you sample so that you have point sources or point antennas, and this also explains for you why the antenna pattern of array repeats itself. You have it also in the digital signal processing. You have always periodic phenomena or periodic behavior. What you know also in the digital signal processing as aliasing, okay, it is also in the antenna arrays here is defined as grating slopes, or that you repeat yourself many times. Okay, but whether we have a discrete point antennas or continuous, more or less we are the same. The continuous is something like analog signals. The discrete is digital signal processing. Okay, you have already noticed that the wider the antenna aperture, the smaller or the narrower the point spread function, which means the better the resolution. SAR, instead of having, and by the way, if you look to what is called wide or narrow, as I told you before, it is always in terms of wavelength. Because if we say that we agree that we will have the separation between adjacent antenna elements lambda by 2, so if you have 100 elements, so you have 50 lambda. So 50 lambda by 1 megahertz are not 50 lambda at 10 gigahertz or in terahertz. You may have a very, very nice antenna array with extremely high directivity at terahertz, which is so small. And if you multiply, because the frequency scales, so you need maybe a football yard in order to have the same performance at much lower frequencies. Okay? Another way of thinking, or another implementation of antenna arrays, which helps as having a very, very big antenna aperture, is to have a single antenna and to move it. Because what is antenna array? I have individual antennas placed statically at certain points. The question now, why not? I have only one antenna, and I will move it. I will have a measurement here, okay? And if everything periodic, because I work monochromatic, I will measure the next period here, the next period there, and I go back and forth in 2 dimensions as wide as I wish. Therefore, and this is actually synthetic. Synthetic aperture, the aperture itself is not physical. This is actually created by moving a single antenna. At each position, the antenna itself is an element, and you collect data, and now you deal with the data as if they were coming from a real antenna array. And in this case, you can increase the aperture arbitrarily, because it depends how far can you move freely. And almost all applications using SAR, they use aeroplanes or satellites. If you have satellites, the high resolution satellite image are caused by SAR effect, because the satellite itself, it goes over very, very wide area, okay, and each position represents as if you cover the Earth by an antenna array. And you can imagine now, you can calculate very, very easily at this frequency with this distance, how much resolution can I have. SAR is clear. So this SAR is not more and not less than a single antenna, whether receiving or transmitting, which moves in 1 dimension or in 2 dimensions in order to synthetically create an array. Okay, what are the technological problems related to that? It is actually the stability, because you should, as an engineer, think, I'm standing here and I decide to capture the signal when I'm receiving or to send the signal. Okay, now I save this, I register this in a record, and I go to the next position and I do the same. I must synchronize, so I have a synchronization problem. Any deviation from the synchronization will cause artifacts. Okay, we spoke about the artifacts, because imagine this could be equivalent to you let the element of a real array dancing about its position, because you measure here, actually you are assumed to measure exactly here, but because of some inaccuracy you are a little bit right, a little bit left. Okay, so now your artificial array is dancing. Okay, maybe in this direction, maybe in this direction. This is just one problem which you can face in when you do this synthetic aperture. Another one is, especially in the space, how can I locate my position to a reading? Because if I have a static array, okay, the positions are constant, and I know I take the reading from here, from there, and I know this reading corresponds to x1, y1, x2, y2, and so on. Now, when I move, you have another problem, because how can you locate yourself when you move? Maybe it sounds as if it were an easy problem, but if you look to the actual application or to the practical implementation, you will find out it's very, very tough. Your GPS nowadays, which you use in car and so on, helps us a lot. But nevertheless, we have also some tolerance. The cheap application for location, in order to know my location, is using accelerometer. Accelerometer, you know, if you integrate the acceleration twice, you have the position. This is actually the most cheap one. So we just measure the acceleration and integrate it twice. And this way of positioning is very inaccurate, because, as you know, in any integration you have an integration constant. And if you have a very, very small error in the first integration, this error is integrated. So at the time you drift. So the cheap way of positioning suffer from lots of problems, and you have to recalibrate and so on. Or if you have a satellite, it should receive continuously its position from other satellites. You may also say, okay, why not? I know my speed, and I can use the time as an indication for the position. But this assumes that your speed is constant. If your speed deviates from the constancy, so your error in the position is now proportional to this error. So just to think about some problems related to synthetic aperture radar. The concept itself is very simple. Okay, I will move, but how to implement it is really very, very challenging. And I will show you in this presentation some of these challenges. Okay, back. So the presentation was prepared by the first author who finished his PhD 5 or 6 years ago. Therefore, it corresponds to his logic, not to my logic. So, but I will try to put it in my context. So these are two applications for ground penetrating radar. Just if you know the application, you can understand what is ground penetrating radar. I would like to penetrate into the ground. It's exactly one-dimensional problem, okay, like we discussed before. And some application is subsurface objects, anything which buried below the Earth's surface, beside detection and identification of anything which is hidden, which is not seen. So this is the definition. You have soil surface, you have something which is hidden below the soil, you have a transmitter and you have a receiver like we showed before. Before continuing, can you imagine what are the challenges which we should expect here if we have such a problem here? In the context now you know what is one-dimensional imaging. Let us assume it is one-dimensional. What are the challenges here? One of the challenges here is this surface. Because if I draw it as a line, it's nice. But if you have a real ground, you cannot have a good estimation of whether it is over a big area, whether it is really plane or it has some variation with respect to the plane. Of course, if you are working in a small size, it's not a big story, because you can say, okay, it is planar. But if we connect this with SAR, which means I would like to raise the resolution, and therefore I must cover big areas, I think you can understand now that this could be a challenge. Because how can you guarantee that this surface is a plane over a wide area? So this is one of the challenges. The second challenge is I'm targeting this thing here. If I don't know the background, in this case, if I don't know the background, I have to image both, because I would like to image the background and the body itself. And of course, this will take time. So therefore, I would like to have here a good model for the background, just to assume the background. If the sand itself is wet, or if you are working in deserts, so it is dry, you should have some information about the background in order to detect this. Okay, good. This is first the definition within the framework of what we, let me make all readable. These are some applications for ground penetrating radar. Geophysical research to know the Earth history, to know whether you have which materials, which minerals, and so on. You have also the geological survey to see the Earth structure for oil fields and so on. You have what is called Borehole Radar. This is very, very important because it is important for oil companies and they are rich. Anyone who is rich is important. So therefore, if you develop something for them, you can have lots of money. So this is, I think I told you once before that when you are drilling, you can at the same time have information about the soil using also imaging. And this is also belongs also to ground penetrating radar because you are actually going into the ground. Crack detection, especially in highways, in the streets, or in buildings. Sometimes, and this is in order to avoid failure. In order to avoid, I think I have to bring my cell phone far away because this is annoying here. So you must detect regularly the health of the structure. I can give you an example just to indicate the importance of maintenance. In Germany, we had 2 high floods in the city where our university is, once 2002 and once 2012. And were so high that many houses were destroyed and it was a real catastrophe. And one of the reasons for the extreme damages was there is what is called I don't know the English name, but in order to protect an area from high flood, you build something like a mountain of sand. It is not dam. I think it has another name because I was recently with my brother in Houston and they had a catastrophe there. They call it something else, but let us call it dam. And there are some small animals. They build their houses inside, and they make holes and tunnels and all this stuff. And all of a sudden, so many years we didn't have flood, so everything is okay. And all of a sudden you have the flood, and you think you are protected, and it's actually something which is really destroyed because of these animals, because of the many tunnels inside the dams. Therefore, since that time, they decided to have regular inspection, and we used our system, which I am going to show you here, just to put it in a flying platform to Mixar. Flying platform. We were one of the first who worked with this microcopter or this with 4 propellers. Our problems were concentrated in the synchronization. How can you relate a reading of your antenna to a certain position with high accuracy? Okay. Of course, archaeology is, if you look for some statues from the past. Forensics, this is actually for the police to look for criminals and so on. And much more important is this one here. This is the anti-personnel landmine. You know that at least in Yugoslavia, in the 90s, they had a civil war, and you have millions of mines hidden in the ground. The same in Iraq, Libya. So actually, there are many countries with this problem here. And in order to detect mines, the mechanical way is to send the tank. The tank itself, it goes over the mines and let it explode. This is sure. But sometimes the mine itself is placed in situation in a position which cannot be exploded mechanically. And now you think, okay, everything is safe. Okay, let us release it to farmers to work and so on. And now he digs, and then it explodes. Therefore, such a research, ground penetrating radar for mine detection, is not intended for detecting the mines, but for detecting those mines which were not exploded by the mechanical way. Whether in the past they sent donkeys just to go along a road, and they were the victims, and then the people came behind them. Okay, I talk about the direct problem and the inverse problem. This is here a summary. Let us have, this is a buried object and this is a measured data. So actually direct problem means I know everything. I know the ground, I know the buried object, and by solving the direct problem I can expect, or I can find out what are the measured data. In the inverse problem I measure and I try to retrieve. So the direct definition, incident field and buried objects are known, and scattered field is calculated. Whether you have a form for that, you make some analysis and you have analytic form, closed form, or you say, no, this is too complex for me, let CST or HFSS make it for me. So in both cases you have the same. We covered also here two problems which I mentioned yesterday or the day before, the ill conditioning and the ill posedness of the solution. You still remember, imaging is always characterized by either no solution or stable single solution or multiple solution, or what is called unstable. It looks like stable, which means you invert the matrix and the matrix seems to be invertible, but actually because the conditioning is bad, so your solution is very, very inaccurate. But we covered this yesterday, and it is the same definitions. It is here only related to ground penetrating radar. And I hope that meanwhile you understand now these issues, at least in the context of the imaging we presented. Okay, in the same context of ground penetrating radar, we distinguish between range resolution, which we considered in lots of details the last couple of days. This is the depth resolution. It's called range resolution in the radar community, because in radar you have the range and you have the cross range. Therefore, the radar community say this is a range resolution and this is a cross range resolution. In imaging we call it depth resolution, because you go inside, and the transverse resolution. But you know, it's actually only naming. You have the range resolution, which in GPR it is a vertical one, because you go into the ground or the up-down direction, and the cross-range resolution or lateral resolution. The first one, as we see before, depends on bandwidth. The higher the bandwidth, the better the depth resolution. This one here has nothing to do with the bandwidth. It depends only on the how big the aperture is. I think now you can understand what is GPR. It is a three-dimensional. Now I use the bandwidth for the depth, and I use the SAR concept, moving my sensor, moving my transmitter and receiver over the ground, in order to have big antenna aperture, in order to have SAR, in order to increase the lateral resolution. Now we combine both. We have a three-dimensional with the wider the bandwidth, the better the vertical resolution. The wider the antenna aperture or the area over which I am scanning, the better the lateral resolution. The concept is clear. GPR itself is just imaging technique. It's only to put the system or look the system looking into the ground. By the way, we cooperated once with the University of Mississippi, and it was 2008, and the colleague there was working in a project which was called looking through wall. You may find many literature about looking through wall. You would like actually to see what's happening beside you. And then we had our equipment for GPR, and we could have looking through wall by just rotating our antennas and the whole system 90 degrees, and we could have very nice pictures from the other side using exactly the same algorithm, exactly the same antennas, exactly the same. Which means GPR is just, it is actually not the system, but it's the application. The system itself can be rotated 90 degrees, and you have imaging. You have an imager. So we have the imager. The imager itself depends or relies on big antenna aperture to increase lateral. In this case, this is a lateral if it is looking through a wall, and the range is inside. Or you rotate it 90 degrees and you have GPR. Only in GPR or looking through a wall, just another challenge just to think about it as engineers. Usually, if you send a signal through the wall or through the ground, you get first a very strong reflection due to the air-ground interface or air-wall interface. Okay? Say 90% or 80%, very strong reflection. The penetration itself takes place, and it goes and collects information and comes back. Now you have a problem which we didn't consider before, which is a dynamic range. You have, say, the total reflection is a sum of two things. One is very big, and one is very small, which contains the details. And now we come to another attribute of measurement systems, which we didn't consider before, the dynamic range. Which means when I measure, do I measure over 100 dB? Which means the difference between the highest signal I measure and the weakest signal I measure is something like 100 dB. This is the definition of dynamic range. Okay? So if you have low dynamic range, you bring your dynamic range now either around the high reflection. If you can cover, it's okay. So you can cover actually from the most strong to most weak. But if you have a finite dynamic range, you must move until either you have details around the big or the details around the weak. So one says, or the language itself, the big initial reflection masks, it hides the details behind. And in order not to have headache of that, there are methods for subtracting this big amount of reflection. So you say, this is actually also signal processing. So you can say, okay, let me assume first that I don't have an object. I have air-sand interface. And I calculate the reflection due to air-sand interface. Okay? And I subtract it from my measurements. So in this case, I get my measurements clean. Or if it is not exact the same, at least you have damped or made the difference itself as small as the others. And you can, with what is called time windowing, because if you look to the data from the time along the time domain, you see the first reflection comes here, and the other reflections comes later. So you can say what is called time windowing. It is not the windowing we talked about before in the antenna and so on. It is windowing in allocating or assigning different measurements to different objects. Okay? Again, what we discussed before, I'm just repeating. This is the resolution story, which we, as you see here. But I think, let me we calculated as 1 over twice b, I think, maybe because of the factor 2. I don't remember now. And this is actually, we covered this before. So you know what does this mean regarding resolution. And this is actually the point spread function. And this is here related to the range. And in this case, the bandwidth itself dictates the resolution. Here, the cross range and the antenna pattern or the beam width plays the same role like the sink. And I think we talked about that before. But here, he takes, or he distinguishes between the antenna pattern of a single antenna, which we are going to use and to move to create the synthetic aperture, and the what is called in the antenna community the array factor. In the array factor, I just refresh your information. Array factor, we assume that your unit antenna is homogeneous or isotropic. Isotropic, as if it were a point source or point receiver, in order to have the array factor. Do you remember? Or okay, but don't forget that you multiply the array factor by the unit pattern. So the unit pattern itself, for array application, you really don't need to have high directivity unit pattern, because the high directivity unit pattern deteriorates your array factor. So it's better to have omnidirectional antenna, say, as a unit, because the directivity, you don't get it through the unit antenna, you get it actually through the array factor, through the big aperture you created synthetically. Okay, so again, as a rule of thumb, the resolution in the range is proportional to 1 over the bandwidth, and here to the aperture, the antenna aperture. Good. Now, the main work which we conducted here. We wanted to make images of these two forms. Do you remember the American F1? American airplane F1? This form here is designed to minimize reflection, to minimize what is called radar cross-section. So you can, if you are antenna expert, so you know that there is what is called antenna cross-section, a radar cross-section. This is if you have a target, how does this target looks like? How big is it on the screen? This is the radar cross-section. And the idea of this F1 was to have the wings in this case, and you can prove that the scattering at the different edges here cancels each other, so that actually the whole object will reflect minimum. And this is another form, and these two forms were used from styropor with epsilon r something like 1. Of course, we have a contrast here because sand has epsilon r of something like 3. So we have the contrast here. But the contrast itself is not so high. Nevertheless, I will show you very, very nice pictures. When we buried these objects here 10 centimeters below the ground surface, 20 centimeters, and so on. Let us first see what, without performing any signal processing. And I will show to you the signal processing which is done is not more and not less than to, more or less, to perform Fourier transform. These pictures here, this is actually what your antenna receives without focusing, because Fourier transform is focusing. Okay, if you let me explain it. I don't think that I mentioned this in the last lectures. If you look to the form of the Fourier transform, you collect data in frequency domain, okay, and now you process them the simplest way of processing is to perform the Fourier transform. From the integration itself, you can see that this is equivalent to focusing at a certain element. If you say we had g hat of t, it was integration of g of t times this point spread function. So the point spread function selects out the part of g of t which is interesting for you. This was a convolution. Okay? So convolution itself is a sort of focusing. Because, again, how have we conducted convolution? We said we take the point spread function as a torch lamp, okay, and go through or along the picture and consider the picture point by point, spot by spot. As if you, instead of saying the whole one, you focus the light into a spot and you go from point to point. And how have we got this? If you remember the relation between g hat and g by performing a Fourier transform. So therefore, these data here are raw data. You just measure and assign what you measured by your antenna array to xy. So if you have strong, and this is what we discussed before, if you have, you can first define what is strong and what is weak. What is hot is strong, what is cold is weak. So this is one of the interpretation. But of course you can have something else. But usually you say, okay, hot and cold. So therefore this is low and this is high. And you use this coding, this color coding, to build or to construct the image. So in this case, this is high reflection and this is low reflection. And this is actually the original object. So you cannot, you know that roughly where is it. But you don't know exactly the shape itself. And this also applies for this edge. By the way, this is the photos here were taken before we bury. This, you don't take the object themselves. They are about 10 to 15 centimeters below the sand surface. If we now focus by performing something similar to what we discussed before, we get something like that. As you see here, so let us now see the artifacts. Do you still remember, as I told you, if you have black-white, and the black-white, because of the finite resolution, you will get a ribbon of gray between the black and white. And this is actually an indication what is the width of your point spread function. And you see it here. So you see this is black or blue or low intensity, and this is high intensity, and you have now this spectrum which corresponds to the gray. I also told you if you have a sharp edge, the sharp edge is convolved now with spot. So the sharp edge, if you convolve a sharp edge with a spot, you lose the sharpness because you'll have something which is rounded, and you can also see it here. See the sharp edges here and there they are rounded. So this is actually the effect of the point spread function. Point spread function. Now it is a lateral one. Okay, because now this is a tomography. It is a surface image. Okay. Look to the data here. You have x-axis is 40 centimeter. We focus at 8 centimeter. So we perform this Fourier transform in order to pick up the depth of 8 centimeter. Okay, but this is actually in our hand because it is a bandwidth, and you can, by performing the Fourier transform, you can say, okay, I am now 1 centimeter. I focus on 1 centimeter below, 2 centimeter below. This is actually the integration which I showed you before. Where would you like to put your point spread function? 1 centimeter, 2 centimeter, and so on. This is one. And of course, you can go from the surface. You don't see anything, and then you see something which is not clear. And when you are at the level of the object, you see it because you focus there. So this is one effect. But the other effect here, the two-dimensional, if we focus exactly at the surface, nevertheless, we will not have the exact image. We will have the effect of the point spread function. This it's called in the optics blurring. So it is smeared out. So the synthetic aperture radar itself is you go with the antenna 40 centimeter in each direction. I will show you now the setup, how does it look like. Okay, now come to the frequency range which we used. For those of you who worked with the waveguides, this is X band from 8.5 to 12.4. This is KU band, I think from 12 something to 18. And this is K band, around the 26. And this is the KA band, which is to 40 gigahertz. For a long time, we had the equipment up to 40 gigahertz. I think, as Dr. Akhtar was with us, we had the network analyzer up to 40 or 50, I think. But later, in the 2000, we bought about another 5 network analyzers, and we go up to 125 or something like that now. Okay. As I told you before, in order to have a good image, you know the background. You must know the background. Therefore, as a priori information, we measured the background which was sent. Actually, you will see the setup. We built a big box, 1 meter by 1 meter by 1 meter. And in order to simulate free space, we backed it with these antenna absorbers, which are used for anechoic chamber. And we filled it with sand. It became 1 ton. And we had problems as we moved, that engineers of the university came and say, stop. We have a maximum load of only 600 kilograms per square meter, and you cannot put this box. We'll show it to you now. And we had to remove half of the sand from the box in order to cope with the regulations. Okay, here these are pre-experiments or initial experiments in order to determine the characteristics of the sand. So this is here as a function of frequency. You have the permittivity as a real part, and this is a tan delta, not the imaginary part. It's really very low loss, but if you add water, and sometimes we added water in order to see the effect of attenuation and so on, the losses become very, very high. But dry sand is low loss, and you have something like 2.5 to 2.6. If you remember that our objects were from styrofoam with epsilon r of something like 1. So actually, we don't have a high contrast. So we can claim that if we have good images now, so you don't have high contrast, and nevertheless you have a good image, this is a good technique. Okay, this is here, not the I told you before, this is only part. This was a wall. I will show you the whole box. This is the mount for the antenna. We used the same antenna for transmitting and receiving. This was one scenario. Other scenario, we use an antenna for transmitting and another antenna for receiving. Okay, this is here a block diagram of first we have the transmitter, we have the object, we have the receiver, and then we take the received signal. Who asked me from the ladies here or from the girls here about we have the RF measurements and we don't know how to evaluate. It is here. So I will show you now maybe an example of how to get the results from the network analyzer and how to process here. The signal processing, and this is the image reconstruction. After you digitize here, so you start to take samples and you perform everything in the digital domain. this is a box which I told you about. So it is 1 meter, 1 meter by 1 meter. Has the absorbers in all sides. He forgot to draw it here, but we have also on the bottom. So we have absorber in the bottom, absorber in all 5 sides. And this is the sand or the soil surface, and this is the buried. And we intentionally made it not planar in order also to see such effect. So over this box, we have a carriage on which we move using a step motor, very, very accurate. As I told you before, the success of SAR depends on the accuracy of relating a reading, a measurement, to the position. Therefore, we use very, very accurate, here in this case, accurate step motor, which moves centimeter by centimeter along the carriage, and then the whole carriage moves centimeter and you repeat. So you can scan in X and Y. Of course, it is much more challenging if we use the flying platform. We put the same, everything here on a flying platform, but it's really a headache because just to keep the stability of the platform, and this is actually the main problem if you put your measurement system on something which flies, you need here the expertise of the automatic control people. So just to keep, to have information about the actual position when you measure. It's not easy. Okay, I think this is here a better picture. As you see here, this is the carriage. We have our network analyzer. We have the holder for the antenna. This is the antenna here. I think this smallest one was in the KU band, in the KA band, up to 40 gigahertz, when I'm not mistaken. I think so. And what do we have here? The moving mechanism here, this step motor. So you have moving in this direction, and you move the whole. Only the antenna here. The network analyzer is not moved. You move the antenna along here in order to have the XY readings, in order to have the SAR values.
Are you measuring in near field? Is it far?
No, it's far. It's far because actually, if you look here, if we are 40 giga, so we have something, if 30 giga is 1 centimeter. And this is here. The length here, if you subtract maybe 40 centimeter sand, you may have here about 60 centimeter, and this is halfway, you have 30, so it's about 30 wavelength. It's pretty far field.
So you directly measure S11, right?
Yes. If you use, we have scenario with single antenna. In this case, we measure S11. This network analyzer was up to 6 gigahertz. It was something like 26,000 euro. I can imagine now you can buy it maybe for 2,000 or something like that. By the way, Anrizio started, we worked together with Anrizio also a couple of years. They wanted to bring the prices for network analyzers down. And if you look to the network analyzer itself, the RF part of it is minimal. You have the signal processing part and the chassis and connection, whatever you have here, USB or all this stuff, and the operating system. This is a computer in addition to the RF part. Okay? So they decided to let the rest your problem and manufacture only the RF part, which can be inserted in a general purpose computer. The computer takes care of all signal processing, and you have only the RF part as a card, as a computer card. And they succeeded. This was 2010 to have a card for something like 7,000 euro, or I think it was $7,000. From which they sell for maybe $70 to $100 as a standalone system. The problems with standalone systems, for those of you who plan to buy something, it's really a very, very big problem. Because in 1998, as I started in Magdeburg, we bought our network analyzer. It was the first one. And we paid about 130,000. I think it was the D mark in the past. And it was just up to 8.5 gigahertz. Okay, and then we upgraded it later for another 80,000 to cover the range up to 40. And at that time, the operating system, the available operating system, and the available processor was, when I'm not mistaken, it was 286. For those of you who are still acquainted with the old generations of processors. And they used as operating system Windows NT3. Okay, good. We worked, we were happy. We inserted the 3.5-inch floppy disks for data and so on. A couple of years later, the operating system is not existing anymore. It is not supported anymore. Even to transfer data, we don't find the 3.5-inch disks anymore. We don't find the readers, this disk reader or the drives anymore. The university tells you, no, you cannot consider this as nothing before 15 years or before 10 years because it is expensive. I tell you about that because it applies to almost all equipment. You buy, especially the very expensive equipment, you buy it now with support, operating system, and all this stuff, and also input-output, whether you have USB or you have Ethernet, gigabit Ethernet, or 10 megabit Ethernet. After a couple of years, it's still too expensive. You don't find support. You don't find anything. And you have to struggle. Okay? And this was also another reason for Anritsu to say, okay, we will sell only the card. You can insert the card, and we will update the operating, the firmware, the operating system for this application. Okay, you can pay a small amount of money, but you have your equipment still working. It's much cheaper. Just by the way, why I told you that? Because this small thing here was about 26,000 euro. A couple of years later, it is, say, maximum of 1,000 or 2,000. But it was portable. So you have a network analyzer. At that time, it was really an invention to have the entire network analyzer in your hand. It was dedicated to working in the field. So we took everything because the other network analyzer is heavy. So we took it, put it on a carriage here. This is the network analyzer. This is a laptop for the signal processing. The whole thing here, and you see here below the network analyzer, you see the antenna here for field measurements, and you go with the carriage this way. This going with the carriage, if you see this here, was also it is not automatic now. It was just to draw lines on the ground, and you adjust the carriage exactly here and there, and you measure with this here the center line of the antenna at this point and at this point. It is primitive, but it is also a prototype, a laboratory prototype. But you could get your image this way. So I think this is here dedicated to another network analyzer, Roda and Schwarz. I remember that this one here was very, very low frequency. It is up to 4 gigahertz because we don't have another one. This is a 4 gigahertz. This is just for what I told you last time, or maybe 2 days ago, about the penetrability. Because if you go higher with the frequency, with 40 giga and so on, you can achieve limited penetrability. Although the bandwidth, the relative or the fractional bandwidth is high, and you can have nice resolution. But you cannot penetrate into the ground for long distance. If you would like now to penetrate, you should go with the carrier frequency. The bandwidth, the fractional bandwidth is a problem, because if you have a fractional bandwidth of 10%, the 10% around 4 giga is only 400 mega, but the 10% around the 40 giga is about 4 giga. So actually, this is here for the penetrability. So to have more penetrability. Okay, this is just to show how the network analyzer works, but this is known for you. This is because the workshop here was dedicated to also people who are, must not necessarily have a RF background. So therefore, this is not for you. This is a comparison between the different network analyzer. This one here, you use it. You use it. This is the early one from, it was called HP also at that time, from up to 40 gigahertz. These are the specifications. Roda and Schwarz, as you see here, it is only up to 6 gigahertz. This one here from Anritio 20. And as I told you before, this also Anritio, I think this was called Vector Star or something like that. This is a stand of 2010, 2011. Now we have another 2 network analyzer up to, I think, 125 or something like that. Okay, for you, this is actually a block diagram of you mix down. So you have, I will show you you have your measurements in a bandwidth. You mix down in order to have it in the baseband. You can mix down either digitally if you have fast, so digital down conversion. At that time, we didn't have digital down conversion. So if you work now around 40 gigahertz and you would like to have the baseband information, you cannot digitize with the 80 giga sample per second, the sampling rate. So therefore, you must work using analog. So real mixer. So you have, say, mix down with 26, 30 giga in order to bring around the IF. Okay, and then if you have fast digitizer, you can mix down digitally, which is called digital down converter. You may see it. Or you may have again analog, so you mix using mixer until you bring now your baseband information in a comfortable frequency range where you can digitize and get the data. So it's just refreshing your information. If you don't have fasty or speedy digitizer, you can apply, and this is actually very, very old technology, which was introduced by HP in the 60s of last century, what's called subsampling. It is something like, imagine that, let me draw it here. Imagine that you have a repetitive phenomena, and this is in the measurements. In the measurements, because your illumination is in your hand, you can excite periodically so that you know that each time you have the same. So you measure something which is something like that, which repeats itself. You don't have fast digitizer. So you decide to do the following. Let us take the first sample you would like to cover here, say with 100 samples. You say, okay, I will fire my digitizer here to take this point. I'm not fast enough. I will wait. Either if I can catch the second sample from the second slice or from the 100. So I will wait because I'm not fast. I will catch the second sample. This is the first sample. I took it here. I take the second sample here. By just shifting the firing time point a little bit. Okay? And then the third sample, it's taken from here. So after a number of pulses, you can have enough samples from the same pulse. But it is very important to have a repetitive phenomena, something which you can repeat. and this is called subsampling technology, was introduced by Agilent, by HP. You know, the Keysight now was called Agilent in the past, and before that it was the HP. They introduced this for sampling oscilloscope. This is just for your information. If you don't have a snapshot information, which you can sample just once, you can apply this in order to have higher sampling or equivalent sampling, but provided that you have really repetitive phenomena. And this is in the measurement, it is possible to apply. Okay, so whether you use now real-time sampling or equivalent sampling, you have now your data in the digital form. You transfer the data using Ethernet. This is here, I think it was very, very comprehensive work to create a database. It was based on SQL. Database which connects the different measurements. Each measurement device has its own IP address. And you have SQL database, not database, it's called data bank. Data bank just to communicate between the different and collect data from here. I really don't understand lots of this informatic work, but the students or the younger people, your generation, I think you are more competent in this than myself. Okay, this is actually for collecting data, storing here, saving here, and so on. You need that. So you need, maybe you may ask somebody who is, say, competent in data processing. But you are an RF engineer. You can say, okay, this is actually the data, and this is the equation I would like to apply, and please do it for me. More than that, I can say. I know that these were also students, but I didn't consider this as a part of their PhD because I'm a chair for microwaves. They can do it, but not as a part of PhD because I cannot present or submit a thesis with a chapter about data processing. Everyone says, oh, you don't understand. You cannot also judge whether this is original or not. Okay, so this is a summary of the measurement. It is monostatic. Monostatic means I use the same antenna or the same position for transmitting and receiving. You may use two antennas, but still monostatic. Important is you illuminate and measure from the same side. This is monostatic. Bistatic means you illuminate from one side and you measure from another side. This is bistatic. And multistatic is if you illuminate a different side, and for each illumination you measure from. This is the most or the ultimate complex way, and this is actually the most trustable for having better results. But of course it needs time, and sometimes the processing time and the measurement time plays an important role. So measurement frequency domain using vector network analyzer, we use what is called stepped frequency continuous wave. Let me tell you something about that. In order to illuminate or to excite the system, you have different ways. What we discussed before is stepped frequency, which means I will switch on my generator. I will generate monochromatic signal. I will wait until all transient die out and the system settle down, and I measure the steady state response. Okay? When I'm done and I measure the steady state, I switch it off at this frequency and switch on the next frequency. Therefore, it's stepped frequency. Wait until the transients die out. Of course, this is fast, but I mean now from the principle. Measure the steady state and so on. So I collect my data in the frequency domain, not in the time domain. The advantage here, you can inject at each frequency enough power so that say the signal to noise ratio, the equivalent signal to noise ratio in the time domain is really high. because the power is in your hand. If you insert enough power, which means I will let frequency f1 works for long enough time so that the amount of power I injected in omega 1 is high enough. And the same in omega 2 and omega 3. And you know from the Fourier relations, the amount of power in the frequency domain is the same like the amount of power in the time domain. So actually, you created very, very quietly, you don't be in a hurry, you created a very, very nice signal with a high signal to noise ratio. And the stepped frequency, continuous wave, therefore, it is preferable than to excite by a pulse. So you can also have a short pulse, inject or insert high power, but this short pulse suffers from say not the same signal to noise ratio and also not the same dynamic range like stepped frequency. For laboratory purpose, this is here okay because you don't insert in your research the time factor. I would like to work fast. I can work now in order to have best situation, and then I can move afterwards to the other one. This is what is called a stepped frequency continuous wave. Monostatic, we called it. And we measure the complex reflection coefficient. Using vector network analyzer, you measure actually both epsilon dash and epsilon. You measure both the real part and the imaginary part because you need also the phase information. Okay, these are the antennas we used. This is here a rich waveguide antenna, very, very wide band, because these antennas here, they are nice in directivity if you have a big flare and big antenna aperture. But as you know, a rectangular waveguide has a finite bandwidth. If you use reached waveguide, this one here, in the reached waveguide, this thing here is really not necessary, the housing here, because in reached waveguide, the field is highly concentrated between the ridges here. And you guide them additionally by inserting a dielectric here. So that you know, as if you have a dielectric waveguide, at resonance, you have the wave decays away from the surfaces. And in this direction here, you have very highly concentrated field here. And the highly concentrated field, it is not a lecture now on fundamentals of waveguides and electromagnetics. You can show that such a horn has very, very nice wide bandwidth. Just the story of this here. This is something which was bought from a company by another institute, and our students, they decided to borrow it. We didn't pay any cent here or any penny, and they measured the dimension and went to our workshop and let it manufacture. Inverse engineering. So as you see here, and I think you were involved in this story. Yes? Okay. This is another type of wideband antennas, because as I told you before, we need the wide bandwidth for the penetration, and afterwards we have this is here such antennas. They are not directive. Important here is the wide bandwidth, especially if you would like to cover the bandwidth over different waveguide bands. So say X band, KU band, and so on. So this antenna has also a story. We had a guest from Russia, Professor Kirov, I think he was called. And he came to us, and this was the result of military research in the time of the Soviet Union. They were very, very advanced in radar and in ground penetrating especially ground penetrating radar. He was working for the army in the Soviet time. And then after the collapse of the Soviet Union, he was working as a professor. So, you know, cooperation between the universities and the army. And then he came with a very, very nice idea. This thing here, you can cut a copper sheet in a triangular form. He didn't want to tell us which dimensions. He said, okay, I will cut it for you. And you make a spiral of it, like that. Oh, this. So you cut it here, and you make a spiral, and you make a hole in this side, and you come with the coaxial cable. The inner conductor is soldered here on the tip, and the outer conductor is soldered here. This is the antenna. And he explained its function as this loop here is equivalent to a magnetic dipole. This small thing here is electric dipole. And I have now electric dipole and magnetic dipole. I have electric energy stored and magnetic energy stored. I have resonance. So, and you can have this resonance over a wide frequency band. So at each frequency band, you have resonance. Because don't forget, narrow band means the pass band, the system is at resonance. And right and left, the system could be inductive or capacitive. But if you succeed to have continuous resonance, multiple resonance at each point, at each frequency, you have this was his explanation, and it was really very, very wide band. This is the signal processing chain, how measurements data, this is for you. This is here the raw data, reflection coefficient. Gaussian pulse shaping, this is just, I told you about the side lobes, whether in the cross range, I have a point, if I don't window, if I have a rectangular window in the frequency, I will have the sink. And in order to get rid of the side lobes, of course, you pay with the width of the main lobe. You can have no side lobes if you have what is called Gaussian window. So Gaussian window, whether it is in the time or in the frequency actual, for the penetration or for the antenna array, or for the synthetic aperture, just to get rid of the side lobes. This is the Gauss pulse shaping. And then you have the carrier removal. It is something like I mix down. The SAR process, because I collect now data from different points, collect them as if they were coming from a big antenna array. And then I perform the FFT. Now, of course, I have now discrete in time and in space. So I have X, Y, and T. T will be interpreted as Z, like we discussed before. This is this background subtraction, which I told you before. If you have high reflection between the air and the ground, you subtract it in order to improve the dynamic range. And this is the image reconstruction. Is here some? Yes. Yes.
Time gating, you assume that you know the location of the target, is it?
Or you see first the picture, and if they are separated, you can do it afterwards. So you see, if you are working now, you collect the data in the frequency domain. You perform the FFT and the IFT, and now you look, something is really in the time is separated. I can say, okay, this is, I can identify it as this, and let us get rid of it. Of course, if they are nearby, it will not be easy. But if they are not nearby, this is the other technique was, okay, let us make a model for this strong reflection. I know it is not exact, but I will subtract it from my measurements so that if it still exists, it is weaker than in the past.
You subtract the frequency domain or the time domain?
It's actually the same because the Fourier transformation is the same. So if you find the model in the time domain, make a Fourier transform and subtract it from the frequency domain data, it's equivalent to subtract also the time domain. Okay, this is here maybe so the order of magnitudes of the distances. So we have.
Sorry.
Yes, sure.
In fact, in a system like this, there will be two major reflections. One is coming from the transition at the waveguide, the horn.
Yes, sure.
The other one is over here.
You are right, because this one here is taken care of once.
Okay.
Okay, so I have my network analyzer, and this is taken care of in the calibration process because I can calibrate up to the mouth of the antenna. Okay, so that all these complication, it is put in the error 2 port.
So you do a normalization or you do a TRL cal at the mouth?
No, it is something like I will put my calibration reference plane on the mouth of the antenna, so that I actually I take all multiple reflection inside and all this into account.
No, sorry.
Yes.
I don't know if it is good to.
No, of course, sure.
See, when you do a calibration, let's say a full 2-port calibration, we do it on the coax plane.
In the coax, okay.
Then we attach another horn.
Yeah.
What you're saying is we do a calibration if it is a waveguide system.
Yeah.
It's much easier to do a waveguide.
Yes. To make it a it's called multi-tier or multi. So you can use, say, the standards of the network analyzer.
The question was a little different. If you are working at a lower frequency where we are using coax system, not really a waveguide system.
Yeah.
Then we can do a calibration on the coax plane.
Yes.
And we don't have a distinct plane in the antenna where we can do a calibration. If it is a horn, it's very easy.
Yeah.
I understand that. Suppose we had this nice looping antenna there, I don't have an aperture, distinct aperture on which I can do a calibration.
I still remember that they did the calibration this way. You can put say metallic plane, because you cannot have all standards in free space. This is one of the challenges in calibration in free space. You don't have through. Through maybe you can have it too, but through you have open, of course, forget it. You have short and you have line. So if we have line, and there is an additional calculation in which you say, okay, imagine that your reflector reflects 80%, because through the side lobes you lose energy in other spaces. Of course, if you have a huge metal plate, but this is not practical. And then, so you include this calculation into your calibration. I know the free space calibration is really not perfect, like working in closed environment, but it helps, because at the end, maybe the magnitude itself, you need the relative magnitude, and over this bandwidth, you hope that say the relative magnitude or the free space effects are flat, whether in the phase or in the magnitude. But you are right; it's not perfect. It's really not perfect to have. This also explains why imaging techniques which rely on magnitude only, like in optics. Optics, you don't measure phase. So actually you measure magnitude. It is the intensity of the light and not the phase of the light. Of course, if you would like to have 3-dimensional and so on, this is something else. But usually, imaging techniques which rely on scalar measurements and not vector measurements are welcome, because everything is simple, and you may use, in order to have the contour or the curve, just a very simple rectifier to get rid of the carrier, and you have the envelope. But vector measurements is really tough. And we do. I still remember in your PhD you used the airline. So actually we didn't measure in free space. We had what's called airline, and we put the slices into the airline for the stratified medium. You can better say than me.
We did some measurement in the phase.
Also.
Only one port, not two.
Okay. Good. So this is actually how how maybe details regarding the point itself where you measure. This is the antenna position, and how can you focus in a certain area. And so also here, a part of this presentation was different way of focusing, because if you would like to focus, the focusing itself is very, very simple. How to you illuminate, and your object itself scatters. And now this scattering is measured from different spaces. In order to focus at this point, you would like to make all these measurements aligned in phase, aligned in time, so that they are added constructively. This is another way of explaining what is focusing. In focusing, you have a scatterer, and this scatterer sends signals in different directions. If you can measure here, there, and you know actually the distance, the delay, because what you measure here is delayed differently from here, from there, from there. So now you measured and you know the delay exactly, and now focusing means, okay, I will delay this by amount, another amount, third amount, fourth amount, and so on, so that if I add this together, I get the maximum from this point, and all others, they contribute by null, by zero. This is one of the explanation of how to focus. And remember how a receiving array works. You receive, okay? Now, if you would like to receive from this direction, what do? You take this reading and take it as it is. This is the ground element, number 0. The next one, you phase shifted by an amount. The third one by double this amount. Because you intend to concentrate your reception from this direction. And you say, okay, if I have something from this direction, it is the difference in the delays in these elements is, say, alpha. I will make it the other way around, so that when I add together, I collect maximum from here. Any other direction will be phased incorrectly, so that it cancels each other. This is the way you can understand the beam of a array, or you understand the focusing. This in free space is nice, because you know the speed of light, and you know the distance, and you can calculate everything nice. But here, if you really would like to focus here, so this is a target, and you are here, and you would like to find out an estimation of the delay here, because you will take this reading and delay it inversely, and the next one. And so within the framework of this PhD, he developed 3 methods. One, assuming that we don't have the Earth, and I am propagating this way, so that I can calculate, this is very simple, calculate the delay this way. Or I assume certain epsilon r, which I measured before. So I have the beam itself tilted, and this is here. I don't remember exactly what was the difference between 3 and 2, but these were 2 approximations, just to have a better estimation of the delay, which I will involve afterwards for my focusing. Okay? So this is again, and this shows here how, so some sort of, I think in the PowerPoint it was really animation, but this is here PDF. I can't animate it here. So let me give. So again, this is special for the work of this PhD or former PhD students. So it is really not so important for this overview. It's again here how to further focus using an antenna, and instead of so in order to have smaller spots on the surface. Good. These are 2 objects here, and this is how you reconstruct them after applying everything, after applying the focusing and so on. Just this is the ultimate goal. And I think they are distinguishable. You don't see any artifact. This is the reconstruction of this edge. Also after applying everything. This is of letter E, of a stair. And of course, this stair, it is very challenging because of this effect of this small radar cross section. This is of cross. This is again of this. This is of a real mine, but not a live mine. It's dummy. This is, he wrote IMS 2011, and he reconstructed IMS 2011, just for fun. I think this was end of presentation, yes. Okay, so I'm done.
So any questions or comments? This is the last presentation from customers. So.
Yes, sure.
Lots of questions. I'm sorry about
No, welcome.
For this technique to work accurately, we need to know the permittivity of the medium.
Exactly.
If it is homogeneous, it is all the better.
Yeah.
But if you try to use this technique in a real world, where the
No,
ground
no.
is inhomogeneous, what kind of accuracy we can achieve?
So therefore, in one of the presentations here, I told the students we should distinguish between quantitative imaging and qualitative imaging. In quantitative imaging, you are perfectly right. So I would like to know it's exactly, and in order to have the color interpreted correctly or the value, because I make use of these measurements. But say 90% of the imaging techniques are qualitative. So we have lots of artifacts. Even if you say we apply here method, your evaluation is really very, very subjective. So it is not an objective. If you see a nice image as a doctor, so and he can distinguish between kidney and liver, or without thinking about whether the data corresponds actually, according to the theory, to the real dielectric constant and so on. Important is to see contrast, is to distinguish between things. So if you now imagine that now you estimated dry sand with epsilon r, which you measured once in the lab, 2.5 or 3 or something like that, and you have an image. Okay, we know that it is not an accurate image, but because our judgment is subjective, important for us for an image is to see here. We are very happy to see IMS, but you see many artifacts here, and here these artifacts. Why it is? Why do we have this here? Why this hole here and all this? But because we judge really very subjective, I'm happy to see 2000, but and nobody will start to think, yeah, it is not exact. This is exactly the difference between quantitative, where I must have, according to the theory, IMS, and I must be able to explain the artifacts within the framework of the theory, which we discussed. Okay, here I cannot explain it. I cannot explain the artifact. I must speculate. I must say, okay, maybe the sand here was higher or lower and so on. So actually, this is the way. Therefore, in most imaging, and it's still worse if you look how companies make ads for their products. I still remember a company in Germany. They wanted to sell indoor positioning system, and it was based on received signal strength. And as we saw how they calculate, and so it was really miserable. Lots of assumption and so on. But they come with well-prepared experimental setup, and you would like to sell it to somebody who has no idea. So he's happy, because also consider the psychology. Actually, you don't go to the expert. Expert is usually poor scientist who is happy when his paper is published and he doesn't think of being manager or something like that. And the manager mentality, he has no idea, but he can sell himself very, very well. And actually, this is a target person. You come and talk with him. He has no idea. He would like just to say, to go to his boss and say, okay, I have now a very, very nice positioning system. And they hide the weaknesses. And both are working together. So if you take this psychology into account, you can explain many, many things. And you can also know which area I'm working in. Should I exaggerate? Should I tell people also the truth? If you look, even if you go to a conference and you attend a paper, nobody tells you that these are the weaknesses and these are the strengths. They hide or underestimate the weaknesses. It is human being. So therefore, whether it's exact or not, or I hide this, or I find an explanation which makes me look nice, whether I lie or not, this is something else. Okay?
Since you are using a single antenna, how do you take care whether it is in transmitting and when it is in transmitting and when it is in receiving?
So either you use time division multiplexing. This is communication now. You send in a time and you receive, or of course, because the transient dies out very, very quickly, so you cannot use time division multiplexing. You should use frequency division multiplexing. And you know, if I ask you now, if you have a system working with frequency division multiplexing, you have a single antenna. Tell me now, as an electrical engineer, how you separate receive from transmitted.
We use isolator.
Circulator or isolator. I may use circulator, okay? Or if I receive within the same line, I can have a directional coupler, and I know that both signals are going within the same if they have the same magnitude. But usually you have a transmission power very, very, very strong. The received are very weak. Therefore, it's better to separate using circulator or something like that. But this is a way you can work at the same frequency and you separate based on the path.
But here it is being taken care by VNE.
Yes, yes, yes. Because the VNE measures actually the reflection coefficient. So it sends a reference signal, it sends a signal, takes a monitor, so a part of it as a reference signal, receive the other one. Vector signal network analyzer is composed of only couplers, just to split the signal here and there and there. Okay?
Use this time switching.
No time switching. It's a vector network analyzer. If you have
the sweep time is fixed for when it's transmitting and then fixed for when it's receiving.
No, because we work with steady state imaging in which you don't have enough time to say, okay, I will excite in this millisecond. When I receive in the next millisecond, all transients have died out and you don't have a signal. So therefore, you must work simultaneously. You must have a steady state, so continuous transmission and continuous receiving, and wait. Of course, the transient here is really very, very fast, maybe in picosecond or nanosecond, maybe you can calculate it. But actually, you are working in the steady state regime where you have at the same time incident signal and received signal. And you separate them either by couplers or if you have a circulator. Okay?
Depends on the antenna aperture.
Yes.
And that determines the cross-range indication also.
Yeah.
So here we have used a horn, so it will have a wider beamwidth. So we will have multiple reflections also.
No, but we use a horn as a unit, but don't forget the whole thing is SAR. So we move. So actually, the entire pattern, the entire point spread function is a product of the unit. Do you remember the antenna lecture? You have the array factor, okay, times the unit pattern. What you say now, whether we use omnidirectional or high directivity or low directivity, this is not essential because the main directivity is coming from the array, from the synthetic aperture radar, from SAR, not from the antenna.
So the resolution will depend on the SAR.
Exactly. So the unit pattern is subsidiary, because if you have the array factor is really very, very narrow, and now you multiply it by a very, very wide pattern of whether it is horn or it is say omnidirectional. So it doesn't matter, because the product itself is still the array factor.
But if each element is omnidirectional, then in order to achieve a narrow beamwidth, more number of elements would be required, right?
Or bigger area, because actually the elements, it is the position at which you stay and measure. Okay? So this is actually the position. And of course the distance is the d in your antenna pattern, and you can relate this to aliasing, to grating slopes, and all what you learned in your antenna lecture, you can apply it here. So you wanted to ask something, I'm sorry. Yeah.
Some other time.
Okay, good. So any other question?
Why do we have used different bands, X, KU, K?
Because this is regarding penetrability, which I told you before. Still, remember, as we talked about the Rodan-Schwarz network analyzer, it has very, very low frequency. I know that from the first beginning that the resolution is not so good like at 40, but I can penetrate deeper at 6 gigahertz. But at 40 gigahertz, I have better resolution, but I may detect objects maybe 10 to 15 centimeter below the floor. Okay? Any other?
Yeah, question, yes. Go ahead. Okay, so I think let's finish here. After we are done, if you see any question you can ask. But before we finish, I mentioned that this was a talk by IEEE MPT chapter. We have some special gift from IEEE.
Okay.
And we also have pleasure here of such a very good director of IEEE. He has been here.
So, nice to see you.
Yeah, nice.
Yeah.
He was
Very nice to hear.
and he was here outside. Now he's director of IIT.
Okay.
When
Okay.
Jalil came here, I
to
was
see
the
you.
head.
Yes, that's him.
And that's the real story.
I will
Okay.
request him to please.
Okay.
Yeah. Somebody to click?
He is recording.
Okay.
Okay.
Good.
Thank you very much. Okay. Thank you.
Dr. Hari should give this T-shirt to Dr.
Okay. Small.
I thought you were going to say good.
Thank you very much. Thank you.
So I will just have a break and then we'll again meet, say, in 10 minutes for this certification. Okay?
Okay, if I'm allowed to say something, it's really very, very nice time we spent here with you. So we'll at the
just after this.
okay. Okay, after handing. Okay, good. Okay, thank you.